we know that we can break the block cipher used in DSA, but we need 16 pairs with chosen input to the cipher, and we couldn't extend this attack yet to the full version, to the version used in the DSA algorithm, because in DSA you have this casable block cipher somehow chained. You have at least 2 invocations of the casable block cipher until you see a piece of output. As a summary, we have written a paper about this, attacks on the DECT authentication mechanism, and this paper will be presented at CTRSA next year in San Francisco. The paper contains a description and analysis of DSA. It contains pseudocode of DSA, so you get everything you need to implement DSA yourself. We have C and Java implementations of the cipher, which will be soon available at detector.org. And we also have a high-performance VHDL implementation for FPGA cards of the cipher. This is not yet available, but it's already running, and I think we are somehow close between 226 to 230 invocations of the cipher per second, depending on the FPGA. This will most probably be available soon. So now I will give over to Ralph.
Okay, so for the DECT standard cipher, we weren't able to find any software implementations. So for DSAA, there are software implementations, and that's how it was reverse engineered now. What's funny is that the ETSI non-disclosure agreement specifically says that you should not try to register any intellectual property, such as patents, on this cipher, which happened in 1993 when Alcatel filed a patent in Spain, which then became a patent later in 1999 in the US as well. And this leaked significant amounts of data on this cipher. Hang on, sorry. So what we learned from this patent was that we're dealing with an irregularly clocked combiner with 1 bit of memory. We have 3 irregularly clocked LFSRs that are clocked either with 2 or 3 clocks, and they are of length 17, 19, or 21, and 1 regularly clocked LFSR of length 23. Actually, the mapping of the lengths was not known at that time, sorry. So we know the length from the patent of all of the registered, but we didn't know which one was regularly clocked. It was just a guess that the last one would be regularly clocked. So they furthermore described how to do the key setup, and they also had this very strange thing where they check whether a register is 0 after 11 steps of this pre-ciphering step, they call it, which is basically blank rounds of the stream cipher where you don't generate output, but you irregularly clock it. And when that happens, they loaded 1 into every register. Why they do it that way, we don't know. Maybe somebody misunderstood how stream ciphers work, specifically LFSRs, because you can check that like in the very first clock already. So then we had people looking at parts of the chip. So the first tricky part was find out which chips actually do implement this DECT standard cipher, because first we found, well, okay, this phone does not encrypt with the space station, doesn't encrypt with the other base station, and well, finally we found something, a combination where we knew that we actually had DSC. So the chips were decapped, they were sent over to FlyLogic, as I understood. There were some strange transport problems which like slowed down the whole process for a long time, and I think they were thought to be lost at a certain point, but then reappeared. So this was done by Starbuck, Carsten Null, FlyLogic, and Mazu, which is Matthias Wenzel. And these guys managed to recover the tap positions of the LFSRs that way. But then there was a problem with the clocking function, because the logic didn't make sense at a certain step in this diagram. So simultaneously, we began getting greater knowledge of this Cytel CPUs, and we found a product that uses DSC as well, and we looked at that firmware, disassembled it, and looked at other firmwares which didn't support the DSC, and basically looked, oh, okay, well, there's these strange instructions that start with D underscore something, and there's something called D underscore LDK, well, might be load key, and we did a little bit of fumbling around with that, and then there were instructions called LDS and WRS. We didn't know what that was at first, but then we tried executing these instructions on certain parts of the memory that we could read out from PCMCI part, and we found that we had patterns that changed in a strange way depending on the number of cycles that we waited. So we were like, okay, this could be actually the internal state of the stream cipher, because you may want to save the internal state so that you can directly start streaming out the frame at the exact same moment, synchronized with the DSC. And because, I mean, key setup takes time, you want to do that beforehand, write out the state, and get it back when you need to write out the frame. So what this allowed us to do was we were able to single step through the key loading of this stream cipher to determine the feedback taps. This was already done by the other hardware people, but just to verify that these were correct, and also because I wasn't able to read the output properly. I tried drawing diagrams from that, but I failed. So then, the next thing was we figured out that we could actually load a state that was not generated by the load key function. We could just load arbitrary memory. And this allowed us to isolate which bits were actually involved in generating the clocking sequence. So by using basically like 1-bit differentials, we found out that this was only a limited number of bits, and we were able to interpolate the clocking functions using a computer algebra system, which is kind of, well, embarrassing because the function was linear, so we could have seen that with bare eyes, but we were just tired at the time. At the moment, we're still missing the output combiner, but that's for the reason because we haven't written firmware for sending yet. This is something that we know that we can do, we can pull it off, but we just hadn't had the time yet. So what we need to do is we need to have one side that sends out a frame in, with encryption and without encryption, and then we will sniff it with another laptop, and then we'll be able to get known plaintext. In this way, we'll be able to get to the combiner function as well. Now, here's a diagram of the DSC. People of you who have looked at the A5 algorithms may find that it looks a little bit familiar, except for the tap positions. And one length of the output registers. And it actually was designed in at around the same time that A5 was designed, so we figure it was designed by the same group of people. What you see in orange are the tap positions for the Galois style LFSRs. What you see in green are the positions that are used for the clocking. So what is done is that each of the registers gets tapped at the middle bit, just like the A5 functions do that. A5 1 and 2, not 3. And then you tap 3 bits of the fourth regularly clocked register, and you get the clock. You get the information how to clock one of the irregularly clocked registers by looking at bits of the other irregularly clocked registers and 1 bit of the regularly clocked one. So this is kind of annoying, because we had hoped that they would just use R4 for the clock control, because then it would have just been a copy and paste attack from A52, and this thing would have been trivial to break. Well, this unfortunately is not the case, or fortunately, whichever way you look at it. And moreover, it has a much larger state than A51, as A51 just has 64 bits of internal state. This cipher has 80 bits of internal state. And this means that we cannot directly transfer these attacks as well. But the short pre-ciphering phase gives us hope. In A51, you have 111 steps before you generate the first output bit that are irregularly clocked. Here, you only have 40. Some of you may say, okay, well, but you step 2 clocks at a time. This doesn't matter. This just, I mean, it's a linear thing, so you can just transform it into another linear function that, into 2 linear functions, one that steps 2 and one that steps 3 times. So this is, the number that is important is the number of clocking decisions, and this is 40 for this cipher. So at the moment we don't have an attack yet on this, but I'm pretty confident that there are people, maybe here in the audience, maybe somewhere else, who will find an attack on this cipher in the next year. I'll be willing to bet money on that. Now, I'll come to something different, which is actually a practical way to attack DECT and, well, get your hand in the cookie jar very deep. There's something called UAK allocation in the DECT standard documents, and this is basically the pairing mode, where you first bring together the handset and the base station for the first time or for the second time or whatever. And in this process you generate a massive secret between the base station and the portable part. But the problem is this depends only on an authentication code, which is usually restricted to 4 decimal digits that is shared between the FP and the PP, and 64 bits of a random value that is generated by the base station. Now, the problem is, where does this entropy come from? So, here's the diagram again. So, this is used, I mean, you have this procedure because of gaps. So this is a generic access profile, which makes all of the more recent DECT phones interoperable with each other. So what you have is you have one step where the fixed part sends a message to the portable part and says, hey, I want to allocate a key. Here's a random number from me, and here's another random number, RS, from me. And in the next step, the portable part answers with, okay, here you have a random number from me, and the result for the random number that you gave me, because I know the same secret key, it's the same authentication code that you do. And in the last step, you have an authentication reply, which depends on the value RS, which is the same value as in the first step, and another value res2, which is computed from the random value that was sent by the portable part, and together with the authentication key. Now, let's look what these guys use for generating random numbers. This is a widely used DECT stack, and this is an example. The problem is it doesn't get much better than this, or worse. I mean, it depends on your perspective. So let's count. There's a 16-bit integer up there, and then there's another 8-bit integer. So this is all of the entropy that they use. So this is 24 bits of entropy. You think, actually it's 22, because some of those values collide. So what this means is we can grab off 2 challenge response pairs, actually triples, because you have RS and RANDF, but we call it pairs, and responses, the rest one, off the air,